In today's lesson, we will be learning about two types of velocity, angular velocity and linear velocity. Before we can talk about angular velocity, which is the speed at which something spins, we need to learn about angular displacement. The first part of this involves understanding that one revolution of a circle is 360 degrees, which is 2 pi radians. It's much easier to use radians when working with angular velocity, so we'll stick to the conversion factor of 1 revolution equals 2 pi radians. Now, suppose an ant is sleeping on the edge of an old stereo album. As the record turns, the ant moves around the circle. The amount of rotation is called angular displacement. So here's our ant sitting on the edge of our album, and as our album turns, notice the ant's moving around. Now, if I were to stop it here and put another ray in, you could see the angle that the ant has moved. This angle theta would be called its angular displacement. Now, let's keep the ant moving. Suppose he goes around the circle not just once, but he keeps going around the circle. That's twice, 3 times, 4 times, 5 times, and he comes all the way back where he started. What would his angular displacement be? Well, let's take a look. Let's go back and look at that. Our formula for that, first off, we need to think about it. It went around the circle 5 times, and each time you go around the circle, it's moved 2 pi radians. So all we're going to do is multiply by the conversion factor of 2 pi radians per revolution. So we did 5 revolutions times 2 pi radians per revolution and ended up with an angular displacement of 10 radians. The variable we use for that is just our typical old theta for the angle. Now when we're talking about angular velocity, we have a little difference. Angular displacement is how much it moves. Angular velocity is how fast it's moving. So it's the speed of rotation. The variable we use for angular velocity is called omega. This is another Greek letter. It's a lowercase, looks kind of like a W. And our formula is omega equals theta over t. Theta is our angular displacement, and t is time. So suppose the album did its 5 revolutions and it did it in 2 seconds. Well, let's see what that's going to do for us. 5 revolutions, there's our 10 pi radians. Now we did 10 pi radians in 2 seconds, so omega is going to equal 10 pi radians divided by 2 seconds. 2 divides nicely into 10, so it's going to be 5 pi radians per second. This is how we find angular velocity. Now let's talk about linear velocity, and let's go back to our record album. So here we are back at our record album, and now we have a second ant. I'm going to get rid of that rotation. I'm not too worried about that. Okay, now what's going to happen here? Linear velocity is if we figured out how far the ants actually moved in that period of time. In other words, if we were able to take that circle, break it open, and string it out, see how far it moves in the same period of time. So let's see if we went 1, 2, 3, 4, 5 revolutions. They get there at the same time. The question then is, which ant is moving faster? Which one do you think? The one at the edge of the label, right here, or the one at the edge of the album, up here? Pause the podcast, think for about 30 seconds. I hope you were right and guess the ant at the edge. That ant had to move a whole lot farther in the same amount of time. Suppose the radius of this album was 35 centimeters. Then the ant on the outside had to move, let's see, 5 times, and each time was 2 pi times the radius, which was 35. That means that that ant moved 350 pi centimeters, because our 35 was centimeters, in 2 seconds, or he moved at a rate of 175 pi centimeters per second. Now that would be an exact answer. If you wanted to take that to a decimal, you could, but that would be an approximate answer. Think about the ant at the middle. Suppose he's only 10 centimeters away. Well, he still went the same number of rotations, so that was 5 rotations times 2 pi radians per rotation times 10 centimeters per rotation. So he actually went 100 pi centimeters, and he traveled that 100 pi centimeters in the same 2 seconds. So he was only moving 50 pi centimeters per second. Think for a minute about the swings that you play on out at the amusement parks. You know, the ones that spin around in circles real fast? And if you're more of a daredevil, you like to be on the swings on the outside. Why would you want to be on the swings on the outside as opposed to the swings on the inside? Well, they're still making the same amount of rotation in the same amount of time, but the one on the inside is covering less distance, so it's actually moving slower than the one on the outside. That's why we always like to get those outside swings. Now, what we have just found is called linear velocity, and there's a formula that we can use to find the linear velocity of an object that is moving in a circle. And this is our formula. Velocity equals the radius times omega, or the radius times the angular velocity. Remember, that's what omega stands for, angular velocity. So now we actually already figured out what the speed of that ant was. The speed of that ant happened to be 165. Did I calculate that incorrectly? I believe I did. This should actually be 175 pi, I think I have a little typo here, radians per second. Now, dimensional analysis is just when you're using conversion factors to change from one unit of measurement to the other. That's the railroad tracks we discussed in class the other day. The same way you did it in physics, the same way you did it in physics. So at this time, what I would like you to do is pause the podcast, go to page 355 in your book, and try problems 6 through 12. Pause the podcast while you do this, and then come back and check your answers. Here's the answers with the work. I actually called the first problem number 5 instead of number 6. I seem to be having a few typo issues today. Go ahead, check all of your answers. Be sure you did it correctly. And there you have it. This concludes today's podcast. Thank you for listening.